So who of you is actually working on flavor physics? Okay, not that many, but anyway. Okay, so I have the pleasure to give 4 lectures on flavor physics here. And just for further reading, I gave you one reference here, which, as you can see from the preprint number, is already 20 years old, but it's oldie but goldie. It's a great introduction into all the technical details of flavor physics, into the effective Hamiltonian, higher order effects, RGE running, and so on and so forth. So this has been written by Andrzej Buras, and as I said, it's old, so the phenomenology is not quite up to date, but all the technical stuff is still great. And then, of course, on the archive you can find many other lecture notes on flavor physics, so basically you can pick your preferred one, also much more recent ones. Okay, so what I want to do in this lecture is to give you some introduction and give you some feeling of what is flavor physics and why do we actually care about it. So flavor physics is the physics of the 3 generations of quarks and also leptons that we have in nature. And these 3 generations, as we have observed, have all equal gauge couplings. So under gauge interactions, they all behave equally. However, they are different in masses, they are different in U-cover interactions, and therefore you have flavor violating effects, and from the U-cover interactions, also flavor changing interactions. So from these U-cover couplings, as I said, you get flavor mixing. Therefore, you get flavor changing couplings, and that's why heavier flavors of a given quark or a given lepton decay into lighter flavors. And the physics of so flavor physics is then mostly dealing with how do these decays take place, how likely or how rare are them, making predictions within the standard model and seeing whether what we measure actually agrees with the predictions. And then flavor physics is of course also interesting because there are certain puzzles related to flavor. So for instance, one puzzle is, why are there 3 generations? In the standard model we have just introduced them by hand. We don't know why there's not just 1 generation of quarks and leptons, but there are 3 and not more or less. And then also we observe experimentally that the masses of the quarks and also the charged leptons are very hierarchical. So the first generation quark masses are at a few MeV, and then the third generations, the bottom quark mass is at 4 GeV roughly, and the top quark mass is even at 170 GeV. So there's about 5 orders of magnitude between the various quark masses, for instance. And similarly, you also have a big hierarchy between the electron, the muon, and the tau mass in the lepton sector. This is something that we also don't understand in the standard model. In the standard model, these are just free parameters, and a priori you would expect them to be at least roughly of the same size. Similarly, also the size of flavor violating interactions in the standard model, which is parametrized by the so-called CKM matrix. These flavor violating effects are very suppressed, which means that the CKM matrix is very close to the unit matrix. Also, that is something that we don't understand in the standard model, and which is something that we hope to at one day maybe reveal within the presence of new physics, which gives us some hint of the origin of flavor. And last but not least, since flavor violating decays in the standard model are so suppressed because these flavor changing transitions, the CKM elements responsible for them are so small, that means since whenever you have an observable which is very small in the standard model, you have in principle lots of space for new physics effects. So by probing flavor violating interactions, we have a very good sensitivity for new physics, even for mass scales much beyond what can be probed directly at the LHC. So even if we don't see anything at the LHC in direct searches, which at the moment seems to be the case, maybe it changes still, but even then, indirect tests of the standard model, such as flavor physics, can help us to tell us something about new physics. So all of these together give us a good motivation to study flavor physics, and this is what I want to do in this lecture now. So we want to start with a few basics of the standard model, just to get us all on the same page and using the same notation. Since you already had a standard model lecture last week, I can be very brief here. So in the standard model, we have a gauge group of SU3 color times SU2 left times U1y. So this is the QCD part of the gauge group of the standard model, and this is the electroweak part with the weak interactions and the hypercharge interactions. And these two are then broken in electroweak symmetry, breaking down to U1 electromagnetism. So this breaking is induced by the vacuum expectation value of the Higgs field. And the Higgs is an electroweak doublet. So it has a charged component up here, G+, and a neutral component, which we can write as 1 over square root of 2 V plus H plus I times G0. And in this Higgs doublet, G plus and G0 are the Goldstone bosons, which are then, after electroweak symmetry breaking, eaten by the W and the Z. And then H, little h, is the physical Higgs boson with a mass of 125 GeV that we have observed. And last but not least, V equal about 246 JeV is the vacuum expectation value of the Higgs. Now, for flavor physics, of course, what is very important are the 3 generations of chiral quarks and leptons that we have in the standard model. By the way, is this big enough, or should I write bigger? Fine, okay. So we have left-handed quarks, Qj, UL, DL, charmed strings, and top bottom. Then we have the 3 generations of right-handed up quarks and 3 generations of right-handed down quarks. And then we also have the lepton sector, Lj, again left-handed doublets, new El and El, new mu L, and new tau L and tau L. And the right-handed charged leptons are ER, mu R, and tau R. Okay, so these are the fermions in the standard model. And you note that there are no right-handed neutrinos introduced here. This is just by construction, because at the time that the standard model was constructed, there was no reason to introduce them. Right-handed neutrinos had not been observed, and they were not needed because at the time neutrinos were believed to be massless. And if you just take this fermion content of the standard model with the U-cover interactions of the Higgs, you can write down, or you can get mass terms for the up and down type quarks and for the charged leptons, but the left-handed neutrinos have nothing to couple to in order to get mass. So at the renormalizable level of the standard model Lagrangian, the neutrinos stay massless. So again, this is just by construction. You cannot really blame the standard model for not explaining neutrino masses, because people just didn't think that neutrino masses are something that is real. Okay. So then, once we have our field content, it's very easy to get the gauge interactions for all these fermions, and those you get from the gauge interaction Lagrangian. So L fermion is the sum over the 3 generations Q bar J I D slash Q Qj So for the covariant derivative, I always put an index with respect to what fermion fields I'm looking at, because that will then define the hypercharge and the charge assignments. J plus dji. So that's the quarks. And then same for the leptons. Okay, and the covariant derivatives, they have the basic structure. So dq mu, for instance, is given as the partial derivative plus a QCD interaction term, I times G strong, TA, G mu A. So TA are the generators of SU3 color, G mu A are the gluon fields. Then we have the coupling to the weak gauge boson, E, G, tau A, W mu A. So these are the weak gauge bosons, and these are the generators of SU2. And last but not least, you also have the hypercharge coupling, I times YQ, G prime times the hypercharge gauge boson B mu. And then similarly, you have, for instance, for the right-handed up quarks, again, partial derivative and QCD interactions. Then right-handed fermions in the standard model are SU2 singlets, so this term is not there, but we still have the hypercharge term, YU G prime B mu. For the down type quarks, it's the same, just with the different hypercharge assignments. And then similarly for the leptons, both the left and the right-handed ones, you can write the same stuff, just with dropping this QCD coupling, because leptons don't couple to gluons. And of course, you also have to replace the hypercharges here. And again, left-handed leptons come in doublets, right-handed ones come in singlets. And last but not least, I also note the hypercharges. YQ is 1/6. YU is 2/3. YD is minus 1/3. YL is minus 1/2. And YE is equal to minus 1. And as I already said in the beginning, when I briefly talked about what is flavor physics and why do we care, as you can see from this, gauge couplings are flavor universal, so the gauge interactions do not care whether we are talking to the first, second, or third generations. So here you can see we're just summing over all the generations, and so couplings of, for instance, a top quark to the gauge fields is the same as the couplings of an up quark. So here we have flavor universal couplings. Okay. So this flavor universality, however, is broken in the standard model once we also introduce the U-cover couplings. And the U-cover couplings are needed because we need fermion masses. Because in the standard model, if you just write down the gauge interactions, you know that you cannot write down the fermion mass terms, because left and right-handed fermions transform differently under gauge interactions. So you need to introduce the U-cover couplings in order to then, via the Higgs mechanism and inserting the VEF into the U-cover couplings, get fermion masses. So the U-cover Lagrangian looks like this. Again, we have a sum over 3 generations, now with 2 indices that are summed over. And we have here a matrix YU with indices ij, q bar I, h twiddle, uj, plus yd ij, q bar I, h dj. Then for the charged leptons, the U-cover coupling is ye, ij, li, h, ej, and last but not least, we need the hand-mission conjugate for all these terms. And here I introduced this h twiddle field, which is just given by basically it's the dual of the Higgs. So it's epsilon times the complex conjugate of the Higgs field. So that is H0, the neutral component complex conjugated, and minus H minus, where H minus is the charge conjugate or the complex conjugated of the charge component and transposed. Okay. And then, once you have these U-cover interactions, you can simply replace the Higgs boson by its vacuum expectation value, and then you can straightforwardly see that you get quark and charged lepton masses from the structure here. So what you get are the Fermion mass matrices, which generically have the structure 1 over square root of 2 times U-cover matrix YA times vacuum expectation value V, and A here is for up quarks, down quarks, and charged leptons. So you see that since we have written here in general some 3x3 coupling matrices, YU, YD, and YE, also these mass matrices are all 3x3 matrices, and of course they do not have to be diagonal in the same basis. And in reality, this is also what happens. They are not all diagonal in the same basis. So we have these 3x3 complex matrices, which we now need to diagonalize in order to be able to work with mass eigenstates that we always want to do when calculating Feynman diagrams and so on. So diagonalize MA. This can be done by using the so-called singular value decomposition. That exists for any complex n times n matrix. So in general, you can write a complex matrix as a product of 3 matrices, AL times MA diagonal times AR dagger. And what are these different components? So from this notation, you can already guess that this matrix in the middle here is a diagonal matrix, and it is, in fact, diagonal and has real and positive entries on the diagonal. On the other hand, these 2 matrices here, A left and A right, those are unitary matrices. So that means that AL or A right dagger times AL or A right is equal to the unit matrix. And now from this decomposition of your mass matrices, you can straightforwardly see how you can get to the mass eigenstate basis of your theory. Basically, you need to reabsorb these unitary matrices into the fermion fields between which the mass matrices or the U-cover matrices were sandwiched. So we need to do a unitary transformation for the fields in order to get from the gauge eigenbasis, or sometimes also called the flavor eigenbasis, to the mass eigenbasis. Okay, so for instance, we have then, well, as you see, I used its generic notation A here for U, D, and E. So now we can split this up again and see, for instance, that the left-handed up quarks can be written as rotation matrix capital UL times U left in the mass eigenstate basis. And similarly, of course, for right-handed up quark, and then also for the down quarks, we have here D left or D right times the mass eigenstate field, and finally also for the charged leptons, we have these rotations. So again, as I already said, these are the gauge, or also called flavor eigenstates. And these here with the upper index M are the mass eigenstates of the fields. Okay, so now we need to worry, well, can we actually make that transformation, and what does it do with the rest of our Lagrangian? Because we are just basically rotating our fermion fields by a unitary transformation, and then we need to see what happens to the rest of the Lagrangian, in particular to the gauge interactions. So if you look into the details, you find that almost all of these rotations actually do leave the Lagrangian invariant. So of U right, D right, E left, where you can really just rotate the whole doublet, and E right, leave rest of your Lagrangian invariant. And that is because, for instance, if you look at the gauge interaction terms of U right, well, you have something like, well, like this, I times D slash U times U right. As I said, you sum over the flavors, something like this. And then, if you introduce this rotation here, basically you can use the unitarity of these rotation matrices, and you can just well, you rotate that field here, you get a U right, yeah, I spell it out, that's easiest. So you have a U right M times, okay, this notation is a bit stupid, so this is the matrix. U right dagger times I D slash U, U right, U right. Okay, so what you can see here is that you're having twice this same rotation matrix, once with a dagger, once without a dagger, and then in between them you have these gauge interactions, but those are flavor universal. So this structure here is just proportional to the unit matrix, so you can just pull this rotation matrix U right through, and then you can use the unitarity of this rotation matrix, and this is just, oops, this is just the same as before. So whether you work in the gauge eigenstate basis or the mass eigenstate basis, gauge interactions just look the same. And this is the same for all these cases here. Now, however, it's not the same for the left-handed quark fields. And that is because you have the charged interactions. So you have the interactions by the W, and there you cannot just cancel the two rotation matrices, because in that case they are different from each other. So if you look at the charged current interaction, you have something like G over square root of 2 times U bar L gamma mu W mu dl. Now, if you do the same as here, you insert the rotation matrices, you get a G over square root of 2 U bar Lm U dagger L times dl times gamma mu m W mu dlm. And now here you see that if these two rotation matrices UL and DL are different from each other, then this is not anymore the unit matrix, and therefore for the left-handed quarks you actually see a change in the gauge interaction by changing from gauge eigenbasis to the mass eigenbasis. And that's why we are making such a big fuss out of this rotation. So this here is just called the CKM matrix, and this combination here is a physical combination. So this is something that you can actually see when you look into charge current interactions of quarks. Now the CKM matrix is conveniently written in terms of its elements as VUD, VUS, VUB, VCD, VCS, VCB, VTD, VTS, VTB. And as you can easily guess, these indices just refer to what quarks are involved in the interactions. So for instance, VUS is the CKM element that parametrizes interactions between the up quark and the strange quark. Okay, so these are the ones that give you flavor changing charge currents. And they are at the basic of flavor physics in the standard model. So whatever flavor violation or flavor violating processes you see in the standard model, they are always induced by the CKM matrix. Now on the other hand, as you can see, in the lepton sector, we do not have any rotation matrices that don't drop out from the rest of the Lagrangian, so no physical rotations, which means also that there's, in the standard model, nothing like the CKM matrix in the lepton sector, and therefore also you have no flavor changing interactions in the standard model lepton sector. Of course, as you may know, once you extend the standard model to include neutrino masses, then you will also run into the similar structure that you have here, that in the quark sector up and down left-handed quarks cannot be rotated independently, and similarly in the lepton sector then the left-handed neutrinos and charged leptons cannot be rotated independently anymore. And that leads to the so-called PM and S matrix that is the analog of the CKM matrix for the lepton sector. So maybe let us quickly note this. If you go beyond the standard model with neutrino masses, then you get the PM and S matrix. But within the standard model, there's just no lepton flavor violation whatsoever. Okay. So once we have the structure, it's also interesting to see how many parameters are in this matrix. And therefore, let us do a quick parameter counting. So as you can see from how we derived this matrix, the CKM matrix, since the two building blocks are unitary matrices, also the CKM matrix itself is unitary. So a priori, you would think that this matrix comes with 3 real parameters plus 6 phases. However, as always, you have to ask yourself how many of these parameters are actually physical, because you know in many cases phases are not physical and you can just rotate them away. And this is also happening in this case here. So how can you do this parameter counting most conveniently is if you do it based on symmetries. So you have in the flavor sector the Yukawa couplings YU and YD, and those are arbitrary complex matrices. So these both introduce 9 real parameters and 9 complex phases. Just for each element you have a real part and imaginary part, or real part and phase, whatever you want to call it. So these are the parameters that you introduce by writing down the Yukawa couplings. However, then you have some symmetries of the Lagrangian that you can use, that we basically used here in order to get rid of some of these rotation matrices. And these symmetries can then also be used in order to get rid of some of these parameters, or reduce the number of physical parameters. So what symmetries do we actually have? So we have this gauge interaction term that we've seen that was flavor universal. So that means gauge interactions have a so-called flavor symmetry, which is a U3Q times U3U times U3D. So you have a U3 factor for the left-handed quark doublets, the right-handed up quarks, and the right-handed down quarks. So all of these can be rotated independently without changing the structure of the gauge interactions. So that means these symmetries can be used to remove some of these parameters from the U-covers. And since all these are unitary transformations, what we get is from these 2 times 9 plus 9, we can subtract minus 3 for each of these factors times 3 plus 6. And then, last but not least, we have to take into account that actually there is an unbroken symmetry even after replacing the Higgs by its VEV, and we have to keep that, so we cannot remove that one parameter corresponding to this unbroken symmetry. And the unbroken symmetry, of course, is baryon number. So this is U1b. So this just corresponds to an overall phase over all the quark fields. So this one phase cannot be used to remove parameters from the U-cover couplings, because the U-cover couplings are not affected by the symmetry. If you just change all the quark fields by a phase, then you're not doing anything about these U-covers. So this, since it's a U1, it's just a phase, so that gives you 0 plus 1. And then, if we do the math, you see that this is 18 plus 18 minus 9 plus 18 plus 1. So overall, you are left with 9 plus 1 parameters in your flavor sector of the theory. Now, what does this mean? We have 9 real parameters. These 9 parameters are the 6 quark masses and 3 CKM mixing angles, and this one phase here is the one complex phase of the CKM matrix. Yes?
Can you just explain again where to get this parameter counting minus 3 times 3 plus 6? Where is it coming from?
So the idea is you write down your Lagrangian, you write down the gauge interactions and the U-cover interactions, and you have all these parameters in the U-cover couplings. And then you check, okay, how many parameters are actually physical and how many can I remove just by doing some field redefinitions. And you realize that if you just do these some unitary transformations of the quark fields, the only thing that you are changing are the U-cover couplings. You're not changing the gauge interactions, but you can affect the U-cover couplings with those. And that means by just doing clever field redefinitions using these symmetries, you can remove some of the parameters of the U-cover couplings without affecting anything else in your Lagrangian. So you're not hurting your gauge interaction terms by any of these, by using any of these symmetries, but you can remove some parameters from y up and y down. And that's also why we cannot use this this residual baryon number symmetry, because that symmetry leaves all of the Lagrangian invariant. So by making just some global phase redefinitions, which this U1b corresponds to, you cannot affect the U-cover couplings. You cannot remove this this remaining phase, because you're not touching the U-cover couplings by rotating everything by a phase. Okay? Good. Okay. So we see here that, well, as expected, we will get 6 quark masses, and then we also get for the CKM matrix 3 mixing angles, also kind of as expected, but instead of this generic, what you would expect 6 phases, it's really just one phase that you have in the CKM matrix. And then with this relatively simple structure of just having 4 parameters in this unitary matrix, there are various ways on how to parameterize this the CKM matrix. And I want to briefly introduce 2 of them, which are most commonly used in the literature. So the first one is the so-called standard parameterization. So in this parametrization, what you do is you decompose the CKM matrix in terms of 3 2x2 rotation matrices. So the first one is the one which rotates the second and the third generation into each other. So this looks like this, with Cij being cosine theta ij and Sij is sine theta ij. So this is a simple 2x2 rotation matrix. Then we need a rotation matrix for the first and the third generation. So that's C13, 0, minus S13, and this is also where the complex phase delta shows up. And last but not least, there's also rotation between the first 2 generations, and that is C12, S12 minus S12, C12, 0, 0, 1, 0, 0. And this mixing between the first 2 generations is often referred also to the so-called Coffeeville mixing, because Coffeeville was the one who first realized that there is quark flavor mixing. So he was the one who noticed that the strange behavior of strange decaying into up by a certain rate and so on was due to such a unitary transformation matrix. So this is just the Coffeeville mixing, and that's why the angle theta 1, 2, or often also sine theta 1, 2, is called the Coffeeville angle. Okay. And what I didn't write down here, delta is a CP violating complex phase. So the presence of this phase delta in the CKM matrix is the origin of CP violation in the standard model, apart from the strong CP problem, which I think you covered briefly last week, but I don't want to touch here. Okay. Now we have this matrix, and it's also interesting to see what the size of all these elements are, and we have a quite good knowledge of the entries of the CKM matrix by now. So experimentally, the size of these elements is roughly like this. So you have 0.97, 0.22, and something like 8.8 times 10 to the minus 3. So these are just the absolute values of the entries of the CKM matrix as we currently know them, at least more or less. Some have some uncertainties. And you can see that we have quite large elements on the diagonal. In particular, this element VTB is extremely close to 1. And the flavor change that involves the third generation, these are all very small. So here you have something of the order of 10 to the minus 2. And for the flavor changing between the first and the third generations, you even have an entry of the order of 10 to the minus 3. For the first 2 generations, on the other hand, well, this is still close to a diagonal matrix. However, this so-called Coffeeville angle, this off-diagonal entry here, is not that small. It's of the order of a fifth or so. So you see that the CKM matrix has a very hierarchical structure, with having something like theta 1, 3 is much smaller than theta 2, 3, and that's all right. Well, let me write it as S. S23, which is much smaller than S12, and that again is much smaller than 1. So this is one part of the flavor puzzle I've told you in the beginning, that we have this very small entries, this very hierarchical structure in this matrix, and in the standard model there is no reason to have such a structure. It could in principle be all order 1 mixing angles, and this is just basically a random structure in this matrix. However, we have something here that looks as if flavor is almost conserved, and we just have these small flavor violating effects in this matrix. Similarly, as I said, we have the quark masses, which are also very hierarchical, and these hierarchical structures in both the quark masses and also the quark mixings seem to point to some underlying symmetry, some underlying flavor symmetry that we don't know or don't understand in the standard model, but maybe some beyond the standard model physics will tell you about this underlying symmetry. Okay.
Can I ask something?
Yes?
This delta you can then choose arbitrarily, like, because if you say experimentally you only get the modulus?
So as I said, this phase delta is what in the end drives CP violation in the standard model. So you have some choice on how you parameterize your matrix, because you can do some phase redefinition, so you can rotate your phase from here to there. So whether I write it here or whether I basically distribute it somewhere else, that's not something I can measure. So I can in principle not measure the phase of a single CKM element. What I can measure, however, is the phase of some combinations of CKM elements, which is then physical, and that is what is measured, for instance, in CP asymmetries. And from such CP asymmetries or CP violating decays, you can then determine what, in a given parameterization, for instance, in the standard parameterization, the phase is. So this phase is actually measured to be something like of the order of 70 degrees or so. So there's also some uncertainty in there, but we also have some measurement of this phase here. Okay. So the standard parameterization is the, I think, most widely used in the literature, and this is also very useful whenever you do some exact computations, because it's an exact parameterization. This parameterization, as you can see from this product of rotation matrices, is explicitly unitary, so you don't have to worry about unitarity conditions and so on. However, if you want to understand the size of some flavor changing transitions just by doing some back of the envelope estimates, it's not the most useful parameterization, because it has these various parameters, and you also have to worry about, okay, how big is S12, how big is S13, and so on. So you don't really have the idea of what's going on in this parameterization. And therefore, there's another parameterization which is more useful for such things, and that is the so-called Wolfenstein parameterization. So for this parameterization, you choose an expansion parameter which is lambda, which is just S12, and that is about 0.22. So you can do an expansion around this parameter. It's clearly smaller than 1. So then in this parameterization, you have the CKM matrix looking as follows. Here you have a 1 minus lambda squared divided by 2, lambda minus lambda, and 1 minus lambda squared divided by 2. And then for the third generation, the mixing with the third generation, you have to introduce additional parameters, because you do not just have this Coffeeville mixing, but you have to just basically check how large are these elements experimentally. So how many powers of lambda do I need in order to get a reasonable expansion? And it turns out that for this element here, you need 3 powers of lambda, so you have some coefficient A in front. times lambda to the third power. And then, since this element has a complex phase, it picks it up from here. It's this phase e to the minus I delta. You can write this in terms of rho minus I eta. So rho and eta are also real parameters. So this in total gives you a complex phase. And then this term down here, VCB, is not that strongly suppressed. So here you only need 2 powers of lambda. Down here, VTB is very small to 1. So in this parameterization, it is actually equal to 1 up to higher order contributions. And then down here, you have A lambda cubed times 1 minus rho minus I eta. And here you have minus A lambda squared. And then, of course, this is not an exact parametrization. This is also not even exactly unitary, but you need to include higher order effects once you want to be more precise. So as I said, since this is not even unitary, you have to be careful when you want to do calculations, because then at sometimes some terms which should drop out because of the unitarity of the CKM matrix don't actually drop out, and you keep some higher order remnants in your calculation. So never use this when you want to do concrete numerical calculations, because you will certainly screw up. However, for making estimates, this is very useful, because you can then basically do countings of how many orders of lambda you have for a given flavor changing transitions. So this is a very useful approximation for estimating size of a given flavor violating transition. And that will then give you something. You do your counting, you find that, for instance, say your transition is suppressed by lambda to the 4th power, and this you would then call 4 times Habibo suppressed. So if you have some transition which goes, for instance, by this element VCB, so you have a charge current decay of a B quark into a charm quark, that at the interaction level is suppressed by lambda squared. Then you need to square the amplitude in order to get to the decay width, and then you see that such a decay will be suppressed by 4 powers of lambda, which we usually refer to as 4 times Cabibbo suppressed. Even if this transition in principle has nothing to do with the Cabibbo angle, which was supposed to be the mixing between the first and the second generation, this is just coming from this parametrization here, where we write all elements in powers of this Cabibbo angle lambda. Okay. So now, once we have this unitary CKM matrix, and we roughly know what the size of its elements are, we can actually play a little bit with it and see what we can do with it. And one thing that is very often done in flavor physics is the so-called Unitary P Triangle, which I briefly want to introduce what it is and why it's useful. So you have the unitarity of this matrix, and therefore you have certain relations between its elements, because you know V CKM times V CKM dagger is the unit matrix. So that means, for instance, if you take the elements of a given row, take the absolute values and square them and then add them, they will add up to 1, same for a column. And then if you combine two different rows or two different columns with each other, then you will always get 0, because then you end up in the off-diagonal elements of this unit matrix. And one of these relations that you're getting is that VUD times VUB star plus VCD VCB star plus VTD VTB star is equal to 0. And why is this relation particularly useful? Well, of course, you have many others. Also, well, actually, yeah, 5 others that lead to the other zeros in this matrix here, in this unit matrix. But this one is particularly useful because it gives you a triangle that actually looks like a triangle. And that is because if you count the powers of lambda in this equation, you realize that all elements here, or all terms, are of the same size. So this is order 1, and this is order lambda cubed. So here altogether you have lambda cubed. Then here VCD is proportional, or it's basically just lambda. VCB is order lambda squared. So altogether, again, you have lambda cubed. And likewise here, VTD is order lambda cubed. VTB is just 1. So again, you have order lambda cubed. And that means that this equation actually really looks like a triangle when you draw it. While for many other relations of this type, you have elements of very different size here, and then if you try to draw it as a triangle in the complex plane, it looks very smashed. You're not really seeing a triangle structure. So that's why this is usually referred to as the Unitarity Triangle. So how is this actually done? So in the complex plane, you just use these 3 numbers which add up to 0. So you can draw this as a triangle, which looks something like that. And in order to do that, it is useful to normalize this whole equation by VCD VCB star. So then this one element becomes 1. So that's why we can draw the triangle as going from 0, 0 to 1, 0 in the complex plane. And then the third corner of the Unitarity Triangle is then sitting at rho and eta of the Wolfenstein parametrization. And if you want to know more about what the structures of this triangle are, for instance, how long are these sides here, RB and RT, they are called. So this shows, for instance, that RB is equal to the absolute value of VUD times VUB star over VCD VCB star. So that is coming from the first term here. And then likewise, the RT length of this side is coming from the third term. So you can easily guess what it looks like. You have a VTD VTB star over VCD VCB star. And then also, well, so far I've written this Wolfenstein parametrization in terms of rho and eta. And then also I've written this triangle in terms of rho and eta. But once you do a small adjustment to these parameters, the whole thing actually turns out to be much more precise, because you can introduce the parameters rho bar, which is 1 minus lambda squared over 2 times rho and eta bar is 1 minus lambda squared over 2 times eta. And then using these parameters rho bar and eta bar in the unitarity triangle, then it turns out that actually this whole story is not only true to the 4th power of lambda, but to the 7th power of lambda. So with this you have a relatively precise description of the structure of the unitarity triangle, which you can then test experimentally. Now what is also important are the angles in this triangle, and these are denoted by alpha, beta and gamma. So these are angles that you sometimes encounter when people talk about flavor violating transitions or CP asymmetries, saying that, oh, we've measured the angle gamma in decays of B going into D and K. So then gamma refers to this gamma here. And just to make it even more complicated, since different people work in different conventions, there's not only the convention of talking about alpha, beta and gamma, but there's also the convention of talking about phi 1, phi 2 and phi 3, which is particularly used in Japan. So whenever you look into a Bell paper, for instance, or Bell 2, as you will soon get, then here you have phi 1, phi 2 and phi 3. So I usually use the notation alpha, beta and gamma, but as I said, since some people in our community use the other one, you need to know how to translate from one to the other. Otherwise you don't know what they're actually talking about. Okay, so why is this triangle useful, other than that we can draw a triangle, which is maybe not that super exciting? So the idea is that you can measure various kinds of flavor changing transitions, and those transitions can then be used to constrain the unitarity triangle, or well, in the end even over constrain the unitarity triangle and see if this whole picture even works with having such a simple structure. So the UT can be constrained and even over constrained. By measurement or measurements of flavor violating decays. So how would this work in principle? So you have again your complex plane. Well, you know at least the base of the unitarity triangle at 0, 0 and 1, 0. And then you can measure different parameters. So for instance, there are CP asymmetries that measure gamma. And so these are B to DK transitions in general. So a B meson going into a charm meson and a kaon. And those will give you a measurement of gamma that tell you you're living somewhere in this region here. So this would be, for instance, something that you learn about gamma. Then similarly, you can measure beta, so that's the angle down here, and that since it's related to the phase of this VTD times VTB divided by this VCD, VCB star. If you look closely at the structure, you might realize that what this up here means, or what combination up here is, that is the combination of CKM elements that you get in B meson mixing. So from B0 bar mixing, you can learn something about the right hand side of this triangle. So on the one hand, you can look at the size of the mixing effect, which is given by the mass difference that you get in this mixing. You will get the length of the side RT. So that means you get some constraint which looks like a circle. So this is coming from delta MD. So this is the mass difference in B0 mixing. And that basically constrains RT. And then, on the other hand, you can also measure the p-violating effects in these neutral B meson oscillations. And that will tell you something about the angle beta. Or rather, actually, about sine 2 beta. And that will give you, since you're measuring sine 2 beta, there's actually two solutions. So that would give you a structure like this. So this is sine 2 beta, and that's something you can also get from B meson mixing, but this time the CP violating effects in here. And similarly, you can go on measuring other flavor violating transitions, and in the end, you will see whether or not all of your constraints fit together and give you a consistent result, as I've drawn it here, on where the apex of the unitarity triangle sits. So here you can see, well, of course I've drawn it like that, there is a good overlap. So these constraints seem to be consistent with each other, and the CKM picture is working. And in reality also, if you include the constraints that we currently have on this unitarity triangle, the whole picture of the CKM matrix describing flavor changing transitions is actually working very well. And the unitarity triangle fit, so the global fit, taking all of these contributions together and checking what the best fit for these parameters rho bar and eta bar is, actually works very well. So you have a very decent fit for that. So overall, by now, we know rho bar and eta bar at the few percent level, and we have a very good overall agreement of the global fit. So far for this unitarity triangle and the unitarity triangle fits, which you often encounter when looking into flavor violation. Okay. Yes?
You mean that you have a good overall agreement, so is it possible to resolve this ambiguity for the beta angle, or is it still there? Because it just have shown here that we have two possible solutions for beta.
So there is a slight ambiguity with the you mean the ambiguity between different measurements of beta, or the ambiguity in beta, the direct measurement versus the global fit?
I mean, no, just here the naive picture, just have two beta.
So which of these solutions is the right one? Yeah, that is resolved because so the length of this side RB here, this one, that is essentially given by the ratio of VUB over VCB. So you need measurements of both VUB and VCB, and those measurements will then give you a circle that looks something like this. Well, okay, this is drawn maybe a bit too perfectly, but anyhow. So this is something like VUB over VCB, and this circle clearly tells you that only one of these solutions is the true one, and the other one cannot be the right one up there. So that is resolved by this measurement. Okay, good. Any other questions? No.
Does this only work like with this Wolfstein interpretation like this, or is that right?
Well, I mean, of course, you can also write this just in terms of the standard parametrization. Then, of course, the apex of this triangle is not just called rho bar and eta bar, but it has some structure in terms of these three mixing angles and so on. But of course, you can also do it without using this Wolfenstein parametrization. It's just useful to directly see from this parametrization that you have these rho and eta, or rho bar and eta bar in this parametrization. and then just have these two parameters as parameters of the apex of the unitary triangle. But yeah, in principle, you could use any parameterization. It might just not be the most convenient one in terms of writing what this guy actually is up here. Yes?
Maybe I missed it, but what does the delta MD refer to?
The delta MD is the mass splitting between the two mass eigenstates in B0 and B0 bar mixing. So I just briefly noted it here. I didn't yet really introduce it. So you have these two neutral B mesons. B0 is a B bar and D meson, and B0 bar is a B and D bar. So these are the quark flavors in there. And these two states, due to flavor changing interactions, can mix with each other. So at the quark level, the typical diagram would be something like this. So you have D, B, so via the interactions of the W, which can be flavor changing, you can draw such box diagrams which then introduce flavor changing neutral currents. So that means you have some transitions from B bar and D into B and D bar, which would be such a diagram here. And since if you look at the size of the CKM elements and the structure of this diagram, you realize that the dominant contribution in here is really coming from the top quark, and therefore such contributions, or this diagram is just proportional to VTD VTB star squared, and that's why such kind of effects tell you about the right hand side of this unitarity triangle. So about this part here, which is related to the third term here, the VTD, VTB star. So delta MD, as I said, is the mass splitting between the two mass eigenstates that emerge from the mixing of these two mesons. And then in this mixing, you also get CP violating effects. And the CP violating effects can be measured from some CP asymmetry, which then leads to this parameter sine 2 beta. Okay, good. Okay, so now what I've already very briefly checked sketched down there is the issue of flavor changing neutral currents, which is very important. So these are abbreviated as FC and Cs, which is very convenient because this expression here is rather lengthy. So what's up with these FC and Cs in the standard model? Well, first of all, these processes do not exist at tree level. And that is because, for instance, if you look at the Z interactions with left-handed down quarks, you have something like DLI, DLIJ, gamma mu Z mu times DLJK, DLK. Okay, yeah, mass eigenstates actually. So when rotating your interactions of neutral gauge bosons to the mass eigenbases, you always get some structure like this. and in particular you will find twice the same unitary transformation matrix, because you have the same quark fields on the left and right hand side of your equation. So these two will just drop out, and you see that these interactions are still proportional to the unit matrix even in the mass eigenbasis. So you do not have any flavor changing neutral currents in the standard model at tree level. However, these processes are generated by loop diagrams. As I've already mentioned over there. So if you have some internal W plus minus exchanges in your loop diagram, like for instance I've drawn down there, then you can effectively generate flavor changing neutral currents. So you see you have twice some flavor changing charge current interactions, or actually one of them is flavor changing, the other one isn't. And then you effectively get flavor changing neutral currents which are generated only at the loop level in the standard model. So for instance, well, okay, let us have a look at kaon mixing, which is, well, okay. Yeah, and draw it again, it's better. So for instance, you have neutral kaon mixing, S, D, W, W, D, and S. So it's just the same story as before, just the external quark flavors are different in this case. So this is the diagrams that are responsible for K0, K0 bar mixing. And what you see in here is that you can generate a flavor changing coupling between S and D effectively. And the matrix element that you get from such diagrams looks something like that. So you have to sum over the quark flavors that run in your loop diagram. You have two internal quark lines, that's why you have two sums here. And then you need to write all the CKM elements from the different vertices. So that's V, ID, star, VIS, VJD, star, VJS, and then times some function of xi and xj. And here I introduced the dimensionless parameters xi and xj, which are just the quark mass. So xi is mi squared divided by the w mass squared. And similarly, of course, for xj. So the basic structure of these amplitudes is you have this combination of CKM elements, and then from evaluating this loop diagram, evaluating the integral and the gamma trace and all the stuff, you get some function of these dimensionless parameters, which are the ratios of quark mass squared over w mass squared. Okay.
Sorry.
Yes?
Where is the neutral current?
The neutral current is that once you go from this full theory of weak interactions to an effective theory, so that means you integrate out the heavy particles that run in the loop, you effectively generate some structure that looks like this. So you have S and D and D and S. And there I think it's clear that you have some flavor changing, so you have some S and D annihilation into, S and anti-D into D and anti-S. So there's clearly a flavor changing neutral interaction because these guys all have the same charge. Okay, so once we have the structure here, we can actually simplify it a little bit by using the unitarity of the CKM matrix. because we know that not all of these terms in the sum are independent of each other. But we can use that the sum over I over the 3 quark flavors of V ID star times V IS is equal to 0. So that's just a unitarity condition, similarly to the one that led to the Unitarity Triangle. It's just a different combination. And then, I missed a page? No. And then that means that actually, if all of these functions, f, xi, xj in here, were equal, for instance, if we had all quark masses equal to each other, then this whole structure would simply be equal to 0. And the only reason why this matrix element or amplitude or whatever you want to call it is non-zero is because quark masses are different from each other. So that's why these loop functions f, xi, xj are different from each other, and that's why this sum here does not just reduce to 0. So from this we can follow that Fc and Cs are absent in the limit of equal quark masses. And this statement, actually I've drawn it or shown it here only for a particular one loop case, but you can show that this is actually true to all orders in perturbation theory. So no matter how many loop orders you introduce here, you will always end up with the result that if all quark masses are equal to each other, then this will just factor out. You can pull it in front of the sum, and then you can use the CKM unitarity to reduce these flavor changing neutral currents to 0. So that means that since these Fc and Cs are absent in the limit of equal mass, they have to be somehow suppressed by functions of the quark mass differences. And this suppression effect of flavor changing neutral currents, that you do not only need a loop process, but in addition, you also need to have these quark mass differences in there, is referred to as the GIM mechanism. So GIM for Glashow, Iliopoulos, and Mayani. They found this in 1970. This is the GIM mechanism. So this is one of the very important mechanisms of flavor changing neutral current suppressions in the standard model. So to summarize this, we have a number of suppression factors for Fc and Cs. So one, as I just said, is the GIM mechanism. And then a second one that you can also straightforwardly see from here is that since you don't have these transitions at the tree level, you always get a loop factor. And the loop factor necessarily involves the weak interactions because you have some W exchanges in the loop. So this loop factor will always give you a G squared over 16 pi squared. Then a third suppression for flavor changing neutral currents is just the smallness of the off-diagonal CKM elements. So since the CKM matrix is almost diagonal, whenever you need such a flavor changing vertex in a diagram, this is necessarily small and will give you some further suppression of flavor changing neutral currents. So the CKM hierarchy. And last but not least, another suppression that I just want to mention here, which sometimes appears but not always. And that is related to the fact that we have only left-handed flavor violating interactions, so charge current interactions which induce these FCNCs are purely left-handed. And this pure left-handedness of the transitions, at least in some cases, lead to a so-called chirality suppression. So these are typically cases where either due to final state kinematics or due to renormalization group running, it would be much more favorable to have a transition into left and right-handed quark fields, but the standard model is telling you, no, that's not possible. Everything has to be left-handed, and that is what is often referred to as chirality suppression of FCNCs in the standard model. So this is the fourth suppression factor of at least some FCNCs in the standard model. I would say it's overall a little less important than the other ones, but still it's something that sometimes becomes very relevant. So I want to put it here on the list. Okay, so 2 minutes. Yeah, okay, let me be brief on this. Okay, so now once you have this basic understanding of where flavor changing neutral currents are coming from in the standard model, namely from the flavor changing charged current interactions at the loop level, then you can basically go out and try to make predictions within the standard model for these flavor changing neutral current processes and test them against the data. And since you have such a strong suppression of these flavor changing neutral currents in the standard model, you in principle have a very good sensitivity for new physics contributions, because the smaller your standard model contribution is, the larger will your possible new physics contribution be in relative terms. So it's actually not that difficult to have something like a 10, 20 or 30% or something deviation from the standard model in flavor changing interactions, or flavor changing neutral current interactions in particular, even if you have no new physics around the TeV scale found so far, simply because standard model is so strongly suppressed, and in principle none of these suppression mechanisms have to be present in new physics models as well. So in principle, in a new physics model, you can have flavor changing interactions at tree level. There doesn't need to be a gym mechanism. Of course, once you have tree level FCNCs already, then this whole argument of unitarity and so on is just gone. Then the CKM structure does not have to be present in your new physics model. And last but not least, you could also involve left and right-handed quarks into your flavor violating interactions. So you have in principle this playground to test the standard model very precisely, because these transitions are very small in the standard model. However, you need another ingredient in order to really have a good testing ground, and that is you also need high precision. And in particular, that is the case because until now, we haven't really seen much of new physics in the flavor sector, and so far this whole picture of flavor in the standard model seems to work quite precisely. So we know by the current data already that the deviations in the flavor sector cannot be huge. So maybe there's something at the 10% level somewhere, maybe at the 20% level somewhere else. But that still means that you need to have good control of the standard model prediction. And in order to have this good control of the standard model prediction, there's various ingredients that you need. One thing, of course, is that you need to know what the CKM matrix is, because this always goes into your predictions for the size of flavor changing neutral currents. So you need to know what these guys in here are. Of course, you also need to know what the quark masses are in order to have the loop function right. So, for instance, the top quark mass is very important. But then also, you have other problems in here. And the main problem, I think, at the moment with precision of flavor changing neutral currents in the standard model is that in nature, we do not have free quarks, but quarks are bound in hadrons. So mostly we are looking into mesons, but in principle, you can also look at baryons and baryon flavor violating decays. But mesons are currently a bit better understood, so let us stay with those mostly. So, but still, you bind the quarks in mesons, and that means whenever you talk about a flavor violating meson decay, you not only have to understand this transition at the weak interaction level and calculate some perturbative diagram, including W exchanges and so on, but you also need to understand what is going on in the low energy QCD part of your interaction. So you need to understand how the quarks are bound in the mesons and how one meson transitions into another one at the QCD level. So you have to include all these hadronic interactions, and unfortunately these hadronic interactions for the mesons are happening at very low energy, and that is where QCD is non-perturbative, and that is where much of the uncertainties of flavor physics in the standard model these days are coming from, because you need some handle on the non-perturbative contributions to flavor changing neutral currents, which are, for instance, in QCD matrix elements, in form factors, and so on. And how do you actually pull these factors apart, and how you can deal with these issues, I will continue tomorrow. So thank you.
Now you have mentioned that you have all this low energy QCD stuff, which is also important. So at the end, what did you put for what do you put for the Quark masses if you want to regulate such a process?
So for the quark masses, so the point is that due to the stream mechanism, the only quark so the up and down quark masses are the ones that you do not really need, because they are so small that x up, well, x down anyway not, because we are talking about K and B physics mostly. But the up quark mass is so small that this x up is basically equal to 0. So there, you don't care what the up quark mass precisely is. What you do care about is the charm quark mass, and then of course mostly the top quark mass. And there, well, if you look only at one loop contributions, it doesn't really matter in which renormalization scheme you work. If you go to include higher loop effects, then it's most convenient to do the whole calculation in the MS bar scheme. So this is what is conventionally done. And then you also need to use the MS bar masses for the quarks. And then, of course, you have some uncertainties on the precise value of the mass. So one thing is, of course, you cannot measure the MS bar mass, but you're measuring, well, this something like the pole mass, but there is some ongoing discussion on what you're actually measuring. Then you have to convert this the pole mass or whatever you're measuring into the MS bar scheme, so that again introduces some uncertainty related to alpha S and so on. So there are some uncertainties associated to this, so that you have some uncertainty, I think, of about 1 GeV or so on the MS bar top quark mass. But luckily, at the moment, this is not the main uncertainty in these flavor changing neutral current processes. So other issues are more pressing at the moment than resolving the precise value of the top quark mass. And the charm quark mass is even less relevant, so that really is important anyway only for kaon physics, while for B physics it's less relevant simply because of the hierarchy of the CKM elements. So B physics always singles out basically only the top contribution, and the charm contribution doesn't matter. As I said, in kaon physics, the charm quark mass does matter to some extent, but also there the uncertainty is less important than other things.
Is anyone now? Okay, so I don't understand, if we make the center of mass energy high enough, why are the QCD corrections low energy QCD corrections? why are they not like regular high energy QCD corrections? And also because you said there was a 20% difference between data and the standard model. Is that right?
I said that there could be something like.
Oh, there could be.
Yeah.
All right.
So in the anomalies we will talk later this week, but yeah. So in principle, there is still space for something like 10, 20%, in some cases even more deviations of the standard model.
I was only thinking that 20% corrections in QCD are normal. So why is it low energy QCD and not the perturbative QCD?
So the problem is that the processes that we are looking at are meson decays. So for instance, you have a decay, as I've already put down there, of a B meson going into D and K. So for this process, no matter how energetic you build your collider, the center of mass energy for the decay will always be at the B meson mass scale.
Right.
And that's the
center of mass frame. It doesn't really.
Yeah, exactly. It doesn't matter how you produce your B, whether you produce it at a B factory where you just have the center of mass energy at this upsilon resonance, or whether you go to the LHC with these huge energies. What you care about for this process is always just the mass scale of the decaying meson.
Thanks. Anything else? Okay, so we'll come back at 2 o'clock for the first lecture by Yael, and let's thank Monika again.